In this video, we're going to talk about another application of exponential and logarithmic functions, and that application concerns Lake Coeur d'Alene, which is in Idaho, USA. It's a beautiful vacation spot. It is a very common attraction amongst the locals as well as people from the outside of the state. But it has also been a site of mining activity since the early 1900s, when deposits of silver were discovered in the vicinity of the lake. Now, once the ground or the mineral-rich soil has been processed, whatever was remaining of it was dumped directly into the lake, as you can see here. Starting from early 1900s, an estimated 75 million metric tons of sediment have been dumped into the lake. Now, of course, some of it has traveled down the river, but a lot of it had settled at the bottom of the lake. A number of cleanup operations have actually taken place where the entire river was diverted artificially in order for the bottom of the lake to be exposed and therefore cleaned. It has also allowed for a unique opportunity for researchers to study how the sediment occurs naturally, how it settles naturally, as well as together with the man-made activity. Now, the way that the sediment is studied is one takes a column of measurement from the bottom of the lake. So you literally insert this, in this case glass, generally it's actually metal column, and you can see different layers of ground being collected from the bottom of the lake. Now, the next question, of course, is how do you time those? So how do you know, for example, that this particular layer corresponds to a particular year? And the biologists here have a couple of tricks up their sleeve. So, for example, they use big historical events that resulted in some kind of ecological impact. If you all remember, the explosion of Mount St. Helens, the volcano in Washington state, happened in 1980 and created a big cloud of volcanic ash. Now, this ash can be traced to a certain depth of sediment, and therefore you can certainly claim that that depth corresponds to the year 1980. Same with various radioactive sediments that occurred through some testing or disasters such as the Chernobyl disaster. So all in all, researchers have actually been able to come up with a formula that describes the depth of the sediment, and it is given by this particular function. Notice here that the time t corresponds to years prior to 1990. So year 1990 is 0, and as t increases, the time actually moves backwards. It is important in word problems to pause for a minute before you start doing any math or arithmetic and actually understand what the function represents. So for example here, t, if I plug in t equals 0, I'm going to get, this is going to turn into 1, 1 minus 1 is 0, so the whole thing is 0. So the year 1990, or the year 0, corresponds to the very top of that column. If I plug in, for example, 20 here, what I have is at what depth are we looking for the sediment that occurred 20 years before 1990. So as you plug in the year, the function will give you the depth at which you have to look at in order to see the sediment that occurred in that year. Okay, so the first thing here is to find and interpret d of 20. So of course, this one is fairly straightforward. We simply plug in 20 into our function here, and we can plug the entire thing into the calculator, or let's say Wolfram alpha, and it will give us a number that is approximately 36.2. We're gonna look back at our units. It's measured in centimeters. So that means that 20 years before 1990, which is of course 1970, the sediment that we're looking at is 36.2 centimeters below the surface. So at 36.2 centimeters, this is the level that corresponds to the year 1970. What year does sedimentation of 50 centimeters below the surface corresponds to? So this question is like the reverse of the previous one. We're given the actual depth, so we're looking at 50 centimeters below the surface, and we're wondering what year was that sediment occurring at. So here, the depth is 50, and we are, in fact, after the value of t. Notice that t only occurs in one spot in this entire equation, so we can solve for it using logarithmic functions. Once before, I think I've said that please try to first isolate the term that contains t and then take logarithms, as that will actually make the calculations simpler. So here I would move 155 over at first, so divide both sides by 155. That way they will cancel. Then move 1 over, then you can take logarithms, and in the end you should get the value for t as approximately 29. Now t is in years before 1990, so 29 years before 1990. I should have also pointed out that the reason that t equals 0 corresponds to 1990 is because this research actually took place in 1990, and that's when this function was modeled. After that, there was a significant change in mining operations as well as the cleanup operations of the lake. So no matter what function you come up with afterwards will actually have to be a separate branch of this function. Let's take a look at other parts. Now we're asked to find and interpret the limit as t goes to infinity of our function. So first of all, let's consider this limit. We have 155, 1 minus e to the negative power. You can analyze this directly, or you can rewrite the negative power as the reciprocal, and it might be slightly easier to see the actual nature of the function. So it's 1 minus 1 over e to the 0.0133t. So now as t goes to infinity, this term will go to infinity. 1 over a very large number becomes a very small power, which means that this entire term goes to 0. And then what we have left is 155 times 1 minus 0, so that's equal to 155. This is once again in centimeters. This is as time goes to infinity. So as we go further and further back in time, this is the depth at which the sediment is located. So that means that back in time, back if we go on forever, the sediment that we're looking at is about 155 centimeters below the surface. Okay, so the lowest sediment here is 155 centimeters, and that corresponds to probably when the lake was actually formed. Next, we are asked to find and interpret the derivative of this depth function. So here, let's take a look at how it's composed. It's 155 times something. So you can apply the product rule, but 155 is a constant, so it's better to apply constant multiple rule. We're going to leave the constant alone, and we're going to take a derivative of whatever is in the bracket. The derivative of 1 is 0, so I'm going to write that in, minus, and then it's the derivative of e to the negative power. Remember, the derivative of e to anything is just itself, so I can rewrite that, times the derivative of its inside, which in this case, of course, is just the power. So the derivative of that is simply the coefficient in front of it, minus 0.0133. Okay, and then if you simplify this out, you will notice that you get 155 times 0.0133 e to the negative power that it was at the very beginning. So notice that this minus and this minus actually become a plus, and this whole thing has a positive coefficient in front of it. Next part, between 1900 and 1990, which means between t equals 0 and t equals 100, you're asked, when is the sedimentation settling the fastest? I'm going to leave this question up to you to ponder about what it is that you actually want to maximize here and how, in fact, to do so. For a final part here, we're asked to sketch the entire function. We already have the first derivative, so we're going to run the first derivative analysis, take the second derivative, run the second derivative analysis, think about the asymptotes and the other intercepts. Okay, so as the first derivative from the last page, we have 155. I'm actually going to leave it like this. I'm not going to compute it as a separate number. 3 e to the negative of the same power. Critical points is when the derivative is 0 or does not exist. So let's look for those. The derivative is 0 when it's a product, when one of the factors is 0. Obviously, the numbers here are not 0, so I'm looking for when is this 0. And we've discussed this earlier. E to any power is non-negative, which means that the derivative being 0 produces no solutions. The next case we have to consider for critical points is when does the derivative not exist? And it's the same thing here. We can plug any number in. So this also produces no solutions. That means that this function has no critical points. No local minimal, no local maximum, nothing like that. That doesn't mean that we cannot run the first derivative analysis on it. It's going to be boring number line, but it can be number line nonetheless. So there's no critical points I can put on it, which means that the entire number line is one big interval from negative infinity to infinity. I can still analyze the derivative and the function behavior on it though. That means that I can plug in any number from negative infinity to infinity into the derivative to see whether it's going to be positive or negative. That makes sense too, right? Because this number here, as per our discussion, will in fact always be positive. This is a positive number and e to any power is always positive. So the derivative is positive for all numbers, which means that the function is increasing on its entire domain from negative infinity to infinity. Speaking about the second derivative, so taking the second derivative function, I can apply a similar rule as before, where this is just a constant, so I can rewrite this. 155 times 0.0133 times the derivative of the exponential function, which is itself, times the derivative of the inside. And the derivative of inside is going to be just that coefficient of the power. Here, the situation is very similar to before. I'm going to look for when the second derivative is 0, and I'm going to actually come up with the exact same conclusion, because my second derivative here is once again just a number times e to some power. That's never 0, so I have no solutions here. And unsurprisingly, I'm also going to get no solutions for when the second derivative does not exist. That means that the function has no potential inflection points, so whatever concavity it has over its entire domain. So once again, just so that this looks in line with all of the other examples that we did, we can draw the second derivative analysis number line and plug in any number on the interval from negative infinity to infinity into the second derivative. You notice here that the situation changed slightly because now I have this minus sign in front of the coefficient. So no matter what I plug in, the second derivative will be negative, which means that the function will be concave down on its entire domain. The other things that we normally compute are x and y intercepts, which in this case are going to be just the origin, as well as the asymptotes. For vertical asymptotes, I'm not going to have any here because there's no number which will make this function go to infinity at. For horizontal asymptotes, we've actually computed that on the previous slide where we took the limit as t goes to infinity of our function, and it turned out to be 155. So 155 is our horizontal asymptote. Some of the useful numbers that I probably want to compute the function value at are absent. Normally I would plug in critical points and inflection points, but here I have none. If you want to put some numbers on the board though, we've also computed them a couple of slides ago here. So for example, I know that at 20, the depth was 36.2. So at point 20, I have 36.2. And from the previous, that slide again, I also know that 29 years before 1990, the depth was 50. So here, at least I have some numbers that I can ground myself onto when making the graph. Pause the video here, sketch the graph using all of this information, and see if you can come up with something similar to mine in a second. So you should get something like this, which converges to its horizontal asymptote, starts at the origin and goes through the 2 points that we have in the actual values for. It is always increasing and it's always concave down, which is in line with our first and second derivative analysis. Notice that my scale here is not quite right. Otherwise, the graph would look a little bit wonky. So I put this little bit of a squishy axis here. This is also a really great way of trying to sell the wrong statistics, trying to lie with statistics if you actually mess with a scale on one of the axes. So watch out for that. This is a very standard process by which these graphs or any graph in calculus will be analyzed. So please notice how we didn't change anything about the process of sketching or first or second derivative analysis. We simply are now operating with different functions within the same framework. Once we get to trigonometric functions, this is going to be the same thing again, where the process will not change, but the functions will be different.